Okay, good morning everyone. So let's continue on with chapter 18, which is talking about temperature, heat, and the first law of thermodynamics. Just to recap a little bit, we started off with defining concepts of temperature, and one of the kind of foundations of thermodynamics is this zeroth law of thermodynamics, which basically says that there is such a concept such as temperature. The way it's defined is that if you are talking about thermal equilibrium between two objects, so if you have something, say a third body T in thermal equilibrium with an object A, and it's in thermal equilibrium with object B, then it's A and B are in thermal equilibrium with each other. So basically temperature is something which is an objective quantity that you can define. This is not necessarily a obvious result, sort of obvious to us because, you know, as humans we have temperature sensors built into us, but it doesn't have to be that way, but it is. And talked about how temperature is calibrated using this constant volume thermometer. It's a little bit of a kind of complicated example, but one of the main points is that you know, in order to define temperature, you need some way to calibrate it. And so in this case, we're going to calibrate it with the triple point of water, which has a unique temperature. This only occurs at a particular temperature and pressure, and also the absolute zero. And using this setup, you can basically make a kind of thermometer, and then you calibrate it by basically putting this bulb into systems with various temperatures. So these are sort of some technical details, if you like, but if you want to kind of eliminate the dependence upon the gas or the volume, then you can do some kind of extrapolation procedure. And, well, this is how you would eventually define your temperature or your thermometer. Okay, and there's various temperature scales, Celsius and Fahrenheit. But most of them are basically, well, I think all of them are linear scales. And so these are some real temperature scales. Linear meaning that basically it's only they're only different by some offset, which would be these numbers, or some multiplicative factor of what a unit of, like, what a degree in that scale is. So of course Fahrenheit and Celsius have different units, right? 1 degree in Fahrenheit is different to 1 degree in Celsius, but it's just a constant, well, you multiply it by some factor. Okay. So now we're going to talk a little bit about thermal expansion. So this is probably, again, a concept which is pretty familiar to you. So if you heat something up, it generally expands. That's usually the case. There are some exceptions, like well, water it's a little bit different, but when water freezes, it actually expands. But that's actually kind of an anomaly, really. It's normally not really the case. So normally, when you heat something up, basically the size of it expands. This is why you see such constructions in roads, because of course a road is exposed to various swings in temperature in summer and winter, and so if you don't build these things in, then the roads sort of buckle, and so this is a example of a poorly constructed I guess, railroad. Another application is these are bimetal strips. So sometimes you construct things on purpose so that they change shape with temperature. And so if you stick two materials together, like brass and steel, and then you look at the temperature, if there's a temperature change, then the brass expands more than the steel. And so this is sort of forced to bend. And this might be used as some kind of, for example, like some kind of temperature switch or something, so that, say, there's some switch here, down here, that this metal will actually kind of press, or perhaps it makes electrical contact when the temperature exceeds some value, and this might be some safety mechanism. And so I guess a good thing about something like this is that you don't need something active to measure the temperature. You don't need like a digital thermometer or anything like that. It's sort of automatically there, and it just depends upon the expansion of these materials. So there's a formula of how this works. It's pretty straightforward. So the basic phenomena is that if you've got a length of some material, it will expand by some amount if you heat it up by some number of degrees. Right? So obviously the amount that it expands is, firstly, it's proportional to the temperature change. So if you heat it up by 1 degree, then it'll expand by so much. If you heat it up by 2 degrees, it should expand basically twice as much. Of course, there's a limit to this. It doesn't keep on expanding forever and ever. But within a reasonable temperature range, materials generally behave like this. So each degree makes it expand by a certain amount more. It's also the amount that it expands, this delta L, is also dependent upon how much material you have, right? So if you got like 1 centimeter of some material, the amount that it expands by heating up by 1 degree is going to be less than if you got like a whole meter of the material, right? You'd expect like a meter of the material to expand much more because it's just, it's bigger, or you could view, the thing as being the combination of smaller pieces, right? So the more material you have, the more it will expand. So basically, this formula is just saying those two things, that the amount that some material L will expand, find the, the amount that the material L expands is proportional to the length of the original material, and then also the temperature. The amount that particular materials will expand depends very much on what material you're talking about. Some materials expand much more than others. For example, ice expands quite a large amount compared to something like quartz, which doesn't actually expand very much at all. Okay, so given this, this is a sort of a classic thermal expansion puzzle, or it's a mind twister or something. So if you've got something like this, which is a hole in like some metallic ring like this, right? So if you heat this up, then does the ring's hole get larger or smaller? Smaller. Okay. So if you put something in there, it would actually kind of grip onto the object more. Yeah, make sense? Anybody else? Actually no. Actually, it doesn't. It actually gets bigger. So, what you said is kind of what you'd sort of expect, right? Because, okay, so it expands because, this, it should go like this. This bit goes out, this bit goes in, and then, yeah. But actually, it doesn't exactly work like that. It works a little bit more like what happens if you put something in a photocopy machine, right? So if you put something in a photocopy machine, you've got some, if you've got some, okay, so let's draw the rings first. So basically what it does is to, it's like you put it in the photocopy machine and then you do 120%. Then basically everything sort of gets bigger. This outer ring gets bigger, the inner ring gets bigger, just everything gets bigger. And so, for example, here you can see that the dotted line, this is the expanded version. So the outer square goes out. Also the inner ring also goes out. Same with volume expansion. So in 3 dimensions, it will basically go out in every direction. If you have a metal ruler, everything's same too. So sort of just everything expands out. So volume expansion, okay, so you can also write a similar kind of formula to what we had on a couple of slides ago here about how much the length expands, but let's say we're talking about a volume. And so the volume that something expands, so maybe just to visualize it a bit more, say we've got a cube, and then you heat it up and then it becomes a bigger cube. So the volume expansion, which is basically the change in volume, here's our original volume, V, and here's the new volume, V prime. That change in volume looks very similar to the other formula. So here's the original volume. It's proportional to the temperature change. If it goes up by 1 degree, there's some particular volume change. If it goes up by 2 degrees, then there's the same amount, double the amount. This beta here is just the coefficient, which is again this thing which material dependent thing, right? So it's got units of some value, per degree, right? So this is the fractional amount that it increases per degree. So you might like to think of this as a percentage, right? So this is say 51 times 10 to the minus 6. So alpha of ice 51 times 10 to the minus 6, which is, so 5.1 times 10 to the minus 5. If you want to think of it as a percentage, then it's, so it's minus 3, so I guess it's 0.0051. So this is per degree Celsius. Basically, it expands, the length expands by that amount, that percentage, because this delta L over L is basically the percentage increase, right? That percentage per degree. Okay, and for the volume, you have a similar coefficient here, which will be, again, the fractional amount per degree. But here we're saying it's 3 times alpha, where alpha is the thing that we were just talking about over here. Alpha is the linear expansion coefficient, And when we go to volume expansion, it's 3 times that. So why do you think it's 3 times that? Why should it be just 3 times? Right, yeah, yes, it's related to the dimensionality, yeah. So we can work this out actually using, say, this example, it's easiest to see. So, so volume will be, let's call this L, right? So L, L, L. And what's going to happen when this thing expands is that each of these sides are going to be L plus delta L, right? And then, could we get F2, please? F2. I think you didn't press it yet. Could you press it again? Yep, you got it. Okay, now the new volume is going to be L plus delta L cubed. And if you expand this thing, it will be L cubed plus 3 L squared delta L plus 3L delta L squared plus delta L cubed. And maybe I'll here. So these delta L's are generally some kind of small amount, or okay, well let's view it like this. So this stuff here is basically our change in volume, right? Because this is the original volume, and this is the change in volume. So if we're saying that the change in volume divided by the volume, if we just say use this form here that we've got down here, this is equal to, well, beta times change in temperature, and so this thing is going to be also equal to, that's the delta V. If we divide this by L cubed, it's going to be 3 squared delta L. And then, well, okay, I'll include it now for now. Divided by L cubed. And we've got 3 delta L on L plus 3 delta L squared plus delta L cubed L cubed. But these things are kind of small because basically they are, this is the fractional change, right? So delta L on L is kind of like the fractional change. And so basically these are going to be, this is like the square of the fractional change, and this is the cube of it. And these are kind of small numbers here, right? Delta L on L. Generally pretty small numbers, so we can just say that these are small and forget about them. And then the delta L on L is what we already wrote down over here. So this is 3 alpha delta T. So by looking, this is our definition. And we also worked out here that it's going to be 3 alpha delta T, and so by looking at this one and this one, we can see that beta is equal to 3 alpha. Okay. likewise, if you're looking at an area expansion, you can also write a formula like this. And this time it's 2 alpha because it's like 2 dimensions. A very, very similar argument, except that this thing is going to be squared, not cubed. Okay. All right. Any questions on that part? All right. Okay, so now we're going to move on to kind of a little bit more of the kind of main topic of this chapter, which is talking about heat and work. Okay. So firstly, we've got to define what heat is. We've talked about temperature, which is basically a measure of how hot or cold something is, right? Now, obviously, to change the temperature, you heat something up, or maybe you cool it down. So, heat is actually defined as the energy transferred between a system and its environment because of the temperature difference, right? So, the way we think about heat is that we have some system, say it's cooling down, then what's going to happen is that energy is going to be leaving the system and going elsewhere, in this case the environment. And in this case, the temperature of the system is going to go down. And this basically happens because the system will have a higher temperature than the environment. So if you've got a hot coffee cup and it's sitting there, it will lose energy. The heat of the system will be transferred out of the coffee cup into the environment. And eventually the temperature will go down to the same temperature as room temperature. If you've got a cup of water and it's just room temperature, then there's not going to be any exchange of heat. So there's no heat transfer in this case. Or if you've got a cool drink and you've got it on the table there, eventually it will warm up, of course, because the environment will give the drink, heat energy. So heat is, of course, it's actually it's measured in joules because it's an energy, and basically this is the thing which induces some change in temperature. Okay, here we go. So heat is some properties of heat. So it's not an intrinsic property of a system. It's not that you can say that something has this much amount of heat. It's always associated with a transfer of energy, right? So if you have some two objects, then basically the energy transfer is actually the heat. Doesn't really make sense to talk about how much heat something has. We can talk about what the temperature of something is. That's an intrinsic kind of property. But the heat is actually always a transfer. It's a lot like the our bank account analogies that we did in the last chapter. So remember, when we talk about work is always associated with the transfer of energy between two forms, right? So work was something to do with the transfer of energy. Likewise, heat is also something to do with the transfer of energy. But in this case, the form of the energy is, we're going to be talking about temperature. Because it's an energy, it has energy of joules. And historically this was measured in things like calories and other quantities like this. But in generally what we we're going to use joules, and there's just a straightforward conversion between these two. Okay. So there's a way to relate the amount of heat associated with a particular temperature change. So this is the heat capacity. And again, this is pretty straightforward kind of formula. You can basically just deduce it just from the units, right? So there's a few variations on the same idea. So you can talk about a heat capacity of a particular object. So this is not a material, but maybe, okay, here's my table. It has some particular heat capacity, and then you would measure that in just units of say joules per degree, right? So this one is not like a material dependent type thing. This is specific for a particular object, right? So just say, okay, this table has heat capacity of so many joules per degree, and so if you wanted to work out how many joules it would take to raise it, to raise it by 10 degrees, then you would multiply the heat capacity by a change of 10 degrees here, and then that would be the amount of heat that you would need. The more common type of heat capacity is the specific heat capacity, which is talking about, it's a more material dependent thing. So we're talking about how much heat it would take per degree per gram or kilogram of the material. So this is a kind of table showing various materials and how much energy it takes to raise them by a particular by one degree Kelvin. So this is to raise the temperature of lead by 1 degree. It would so for 1 gram of lead to raise it by 1 degree, it takes like this many calories or this many joules, 128 joules. This molar specific heat is just using a molar. So instead of talking about grams or kilograms, just say a certain number of moles of particular material. And of course it's material dependent, right? Right, and so molar heat capacity is per mole, and basically 1 mole just means a certain number, or 6 times Avogadro's number of atoms, basically. Okay, and we also have heats of transformation. So when something goes through a phase transition like ice melting or water boiling, then what you find if you measure the temperature, say you started off with ice in this beaker, heated this thing up, started off with ice at 40 degrees, you'd stick a thermometer in there, what you'd find is that the temperature is going up, but then when it starts to melt, the temperature actually kind of stays constant for a while, despite the fact that you're heating it up. And then once all the ice is melted, then the temperature starts going up again. And then again, when it starts boiling, it stays constant at 100, despite the fact that you're actually heating it. And so what's going on is that energy is required. So you're definitely adding heat to the system, but it takes energy to change the phase. And eventually it comes down to the fact that these molecules of water, you're breaking, you're changing the phase of the atoms. So going from liquid to gas, all these atoms are now going from being fairly close together to quite far apart. And then so just to go to that phase, it takes quite a lot of energy. So this is the energy associated with changing the phase. And this one, because the temperature doesn't change here or here, it depends only upon how much material you have. So this is always not per degree, but usually per kilogram, or maybe sometimes per mole of the material. So say water, to change, heat of fusion means to change it from ice to liquid water. So it takes 333 kilojoules per kilogram to change 1 kilogram of ice into 1 kilogram of water. Likewise here, it takes 2,200 kilojoules to turn 1 kilogram of water into 1 kilogram steam. Okay. All right, so let's do this one. So a certain amount of heat will warm 1 gram of material A by 3 degrees, 1 gram of material B by 4 degrees. Which material has the greater specific heat? A, okay. All right, so let's just break it down. So specific heat. So if we go, what symbols are we using? Okay, so yeah, so specific heat basically means so C times M times delta T. So it's asking for the specific heat, right? So Q over M delta T. And amount of heat is the same, right? And the amount of material is the same. So the only thing that changes is the delta T. So basically this is either 3. So for material A, it's 3. And for material B, it's 4 degrees. So the specific heat will be bigger for a smaller change in temperature. Right? So because this is in the denominator. Maybe more, well, that's sort of a mathematical explanation if you like. But basically it's, so material A basically only goes up by 3 degrees. So it takes more energy to raise it by 1 degree. You're pumping in the same amount of energy, but so material B sort of goes up in temperature quite easily, whereas material A doesn't go up, so it's kind of resistant to going up in temperature. Or conversely, so to raise the temperature, you kind of need more energy. And specific heat is a measure of how much energy you need to raise it by amount of temperature. So certain materials, if you need a lot of energy to raise the temperature, then you say that that has a large specific heat. So the fact that it doesn't go up very much in temperature is an indication that it's you need a lot of energy to heat it up. So yeah, that's why it's A. Okay. All right. So that's sort of a fundamental thing that we need to know. And then, so this is, now we're getting on to talking about this first law of thermodynamics. So, yeah, so there's an interesting way of thinking about these gases. And you might have seen somewhere that often you characterize the state of a gas with various parameters, such as pressure, volume, temperature, number of moles, right? So maybe the kind of mental image that you often have is you got some container, maybe this box here, got some gas in it, and then the pressure is some pressure and volume and temperature. Now, of course, you know, if you look microscopically at this thing, I mean, okay, you know, this is with the benefit of hindsight. We know that, you know, gases are made of atoms and this kind of thing, right? But such a configuration of gas, you know, if you know it's made of atoms, you know, it should, in order to describe the state of it, you would think that you would need basically information about, you know, say all the positions of all these atoms, you know, the speed that they're going at. So if you were to take a sort of a microscopic perspective, then you should need information about, you know, every single atom, where it's located, how fast it's going, you know, everything about the system. So like a full description of this system. So here's atom number 1, and here's atom number 2, atom number 3, and I would say that, you know, to describe the system completely, you would need, well, let's call it velocity. And so forth, right? So that would be like a complete description of the system. Now, of course, this is like a huge amount of information. You know, if you've got a typical gas, you've got, you know, Avogadro's number of atoms, say, and for each one of them, we need to know like the position, and these are all flying around, so you might say, you know, every moment of time it's going to be in a different state. Now that's what you would expect, but interestingly, what people found is that actually you don't need all that information actually. There's a lot you can actually say with just a couple of parameters, and that pretty much characterizes the state of this gas. And just knowing the pressure, volume, temperature pretty much gives you most of the information that you want to know about the system. So, you know, that's a kind of quite a remarkable reduction from what's really happening to kind of boiling it down into just a couple of essential ingredients. So, this, you know, it's you know, in spirit, it's a lot like, you know, what say Newton did. You know, in principle, it's, you know, if you're looking at how something moves, it looks very complicated, but it's kind of reducing it down into just some essential variables that really matter. But of course, actually, you know, it's comprised of a lot of other variables. So the way that we're going to think about this is that we can pretty much characterize the state of the gas just with these say 4 parameters: pressure, volume, temperature, number of moles. And in a lot of the stuff that we're going to do, we're not even going to change the number of moles, right? So we're just going to fix the number of moles because, well, it's often just sort of a bit easier to think of that situation. So, you have some container containing some gas, and then you might do something to it. Maybe the pressure, volume, or temperature will change, but the number of moles, which is the number of atoms, is not going to change. So, because n is not really going to change, we don't have to think about it so much. So often we're going to even just think of these 3 variables: pressure, volume, temperature, and then that kind of characterizes the state of the system. Okay, so we've talked a little bit about what heat is, but we can also talk about the work done by a gas. So if you remember work, as we just did from the mechanics kind of chapter, work is force times distance, as long as the force is constant. And we can convert this to something which is a little bit more like what we are working with for gases, because the force, maybe it's not totally obvious what the force is, but we've been saying that pressure is going to be something that is going to characterize the gas. So let's convert things to pressure, because pressure is basically quite closely related to force. It's just force per unit area. And if we've got this kind of cylinder kind of system, and so this goes back to we're looking at this stuff because people in the 18th, 19th century were interested in pistons and engines and stuff like that. So this is obviously something that's a bit like a piston, right? So we're looking at some kind of cylindrical object with some movable, slidable kind of piston structure here, right? So this thing has some unit area, like it's got some cross-sectional area, A. And suppose this moves up or moves down by changes in changes in height by delta z. So this is the change in the height of this thing. So maybe you measure it from the bottom here. So this change here is delta z. Okay, so the change in the volume of this thing is, of course, A times delta z, right? That's the change of volume. And so let's stick this into the work formula. Eraser. On the other side of the room. So we've got work equals force times the change in the height. So let's replace this by pressure. So force is pressure times area. And this delta z is actually the change in volume divided by the area. So actually these areas cancel. And so the work is pressure times the change in volume. Well, we started off with this, simple formula talking about force times distance. Now, if you remember, actually work was integral of force with distance. In the case that the force changes, right? So, in the case that the pressure is changing, again, we would need to modify this. We would need to do an integral. So if this is for constant pressure, but for variable pressure, we would do P and then times the change in volume. So we've got to integrate with the change in volume. So this is for variable heat. So say the pressure is changing as you expand, right? Then in that case you'd have to use the integral formula. But if it's constant pressure, then we can just do that. Okay, so we've got our expression for work. Now, a variation on this that we're going to be working with is if we have actually something on top of this piston, right? Previously, so let's look at this. So let's look at this situation where, say, you start with the piston and compressed, and you might have that because you have a heavy mass on it like this, right? So this M. And then suppose you replace this with a lighter mass. So M dash is less than M. Okay, so this is smaller. Maybe I should have drawn this smaller to imply that. Now, obviously, what's going to happen is that because the mass is less, it's going to expand, right? And that process actually already means that the gas is actually doing some work for us because the gas just expanded. And what we just said here is that the work is going to be this pressure times a change in the volume. So if there's a change in the volume, the gas has actually done some work. And, well, you can see that it's done some work, I mean, from a practical or, common sense perspective, because this thing has just gone up, right? So we've replaced it with a lighter mass, but still there's a lighter mass there, and it's just gone up. So the gas has just raised this mass by some height. It's done some work for us. So in that sense, the gas has done some work. Okay, so in this case, basically, what's happening with all these forces? So, the way that this piston works is that it's basically something that balances the forces on the outside and the inside, right? And the position of the piston is really just dependent upon where these forces balance. So, the gas itself is pushing on the piston from the underside, and the force that it's applying on the piston is just P times the cross-sectional area. But of course, there's a force on the other side too. Firstly, there's atmospheric pressure. That's actually pushing it down, so you can't forget that actually we're in a pressured environment, actually. So the air in the room is actually applying a force on everything in all directions. So there's no exception to this piston. So the air in the room is actually providing a force downwards. It's atmospheric pressure here. But also we've got a mass on top. So that there's also going to be a force of mg down. And where this balances is actually when basically these things are equal. After we've taken the mass off, now this mass is a smaller mass here, right? So this force down is now going to be a bit less. And this will expand. This pressure will be also, it should be a bit less because the these things must balance. And so those are the forces that are acting here. But when we're talking about the work done by the gas, we actually don't really care about these other forces so much, because remember that work is a concept that it's a force-dependent thing, right? The work is related to a particular force, and the force that we're talking about is the force provided by the gas within the cylinder. So these other forces are there, But when we calculate the force, work done by the gas, we really only care about the pressure that's inside the cylinder here. So again, the pressure might be changing here, but just say it doesn't change by much, and P dash is something similar to P, then work is again it's P times delta V. Okay. All right. Okay, and so another, so a very useful type of way to visualize and understand things about the states of a gas are these pressure volume diagrams. So these diagrams are actually very useful to understand basically what's happening with the states of a gas. And just as it name implies, so it's just basically a graph of the pressure and the volume. And so, for example, in this previous example, we're starting off with some pressure, P, and some volume, some small volume. Later on, it expands to some larger volume, and then this new pressure, P dash. So that process, for example, would be, say, described, say the initial point would be here, and then the final point might be down here. Okay. Now, why plot these two variables in particular? So basically, these are very useful to summarize it, the states of the gas, because so just to go back a couple of slides, we were saying that the states of a gas can be basically characterized just by basically four variables: pressure, volume, temperature, and the number of moles, right? Now, so you might think that, okay, fine, if we're going to characterize by these four variables, then maybe we need a graph in like four-dimensional space, right? Basically, and each point in that four-dimensional space would characterize a state, a unique state of the gas, and that would be correct. But the thing is that so firstly, with the number of moles, as I said before, we usually kind of fix the number of moles. So we kind of don't really need to think about the number of moles so much because it's kind of fixed, and we can think of each different number of moles as sort of just a kind of different case, right? So this one we can just sort of fix, okay? Now we haven't really done it yet, but as for temperature, it's actually not really an independent variable. So some of you probably have seen this relation of PV equals nRT. So actually, if n is fixed and you know P and V, actually temperature is more or less fixed by this ideal gas equation. So actually temperature is sort of a these are not completely independent variables. The T is more or less determined by the other variables. So basically that just leaves these two as your real state variables. And so this is why the PV diagram is actually pretty useful, because basically the way that you can think of it is that each point in this PV diagram is a different state of the gas. So it's not just merely a plot of, okay, I'm just going from this pressure to that pressure and that volume, the way that you think of it is that each point is a unique kind of configuration of the gas, and what you can do is to kind of explore this space here, and each one of those is sort of like a different it's a different state of the gas. So essentially what you're doing is you're mapping out all the different states that are possible with the gas. So that's why it's actually like a very, very powerful kind of tool to visualize what states, or like what processes are happening in the gas, because each point is a unique state. Right? Also, we just said that work is, P times delta V, but it's also pressure, integral pressure with volume, right? So actually, not only is it a visual map of all the states of the gas, you can actually work out some things just by, say, integrating the area under the graph here, because the area under the graph here is actually equal to the work. Right? So you can actually quantitatively work out some things like some aspects of particular transitions, like the work. You can visualize the states of the gas, and and then we'll see some other examples, but it allows you to sort of understand what the kind of processes that are occurring in the gas line. Yeah. Okay, so let's look at a couple of examples of this pressure volume PV diagrams. So I'm going to go through each one of these sort of one by one. Just firstly, quickly, so these are just various processes going from the same initial to final positions, final states of the gas in the pressure volume diagram, but they go through different paths, right? So just like, you can get from point A to point B, you can go there in a straight line, or you can go some, roundabout way. There's many ways of getting from point A to point B, and if you just say, okay, in the case of this gas, basically, because the pressure and volume kind of specifies the state of the gas, basically it doesn't really matter what path you take. If you end up at the same pressure and volume, you say that it's basically the same state of the gas. And so you can go there in multiple routes, but because the work is related to the integral of the pressure, the volume, the gas will actually do different amounts of work, right? So this is an example where the work will be much smaller than, say, this one or this one, because the area under the graph is very, very small. So despite the fact that the initial and final configurations of the gas are the same, the gas will actually do different amounts of work according to the particular process. So that's basically what this is saying. So you can actually control how much work the gas actually does. Now if you go the opposite way, because if you do this integral in the reverse direction, this will actually be doing negative work. So if you go in a cycle like this, you will actually in the first leg, say you do the amount of work in the area under the graph of the first leg, but because in the second leg the amount of work is less in magnitude, but it's negative. So basically the work that the gas does will actually be the area of this closed loop cycle. Right? So you can actually figure out how much work a gas does in a cycle by finding the area within that loop. Yep.
Because the volume decreases, so that's why the work decreases in the fifth picture.
Fifth picture, yes. Yes, that's right. So in this case, it starts from a large volume and then goes to a smaller volume. So the work done is negative because, so it starts from so we'll draw a piston thing. So it starts from a large volume and then goes to a smaller volume. So there's some gas inside here, right? Now the gas is always pushing this way because pressure is always positive. There's no such thing as negative pressure. So the force that the gas exerts is actually always that way. But if it ends up actually displacing this way, then the force and the displacement is opposite, and then the work becomes negative. Yeah. Okay. So let's just go through each of these one by one, just so you can better visualize like what's really happening. So the PV diagrams are great in terms of abstractifying kind of the process, but it doesn't really tell you what you're actually doing to achieve that process. So I'll just give you an example for each one, what you'd be actually doing. So in this first one, I can't remember if the thing actually said constant temperature, but constant temperature process looks a lot like this for reasons maybe we'll talk about later. But in this case, what's happening is that we're starting from a small volume, high pressure, going down to large volume, small pressure. So certainly it's expanding. Okay, so that we draw a piston where it's expanding, okay, like this, and that would happen, for example, by replacing this mass that you have with a smaller mass, right? So because it has smaller mass, it would expand. And in this case, we're not going to change any temperature of the gas. We're not going to apply any heat or anything like that. All that's going to happen is that we're going to replace this mass here, and then it will expand in this way. And that will actually achieve some work because it's raised this mass by some height. And actually, what we're going to see is that the gas has actually lost a little bit of energy in this process. So we didn't get this for free. The gas actually had to actually use some of its energy up in order to raise this mass by some height. So in this case, going in the forward direction, going from this left to right, the work would actually be positive quantity, just the same reason, like what we're saying here. The force is always upward, and it's moving also in the upward direction, so it has to be a positive work. If we were to go in the opposite direction, like going from here to here, replacing this mass with a heavier one, then the work would be negative. So the work done by the object will be negative, meaning that actually it's going to be a gain in energy. So it's actually going to gain energy in going this way because, so if the work done by something is positive, it means it's expended work. If the work done by the object is negative, then it's actually gained energy. Right? Okay, so that's kind of a constant temperature scenario. Now let's look at this case. So in this case, what happens is that it's constant pressure, and then we go somehow straight down, which is a constant volume. So first it's like constant pressure and then constant volume. So how would we actually do the constant pressure? Well, it needs to firstly expand like this. So the volume needs to go up, right? Yet the pressure can't really change. That's what we're saying here. The pressure should be exactly the same. And this piston is just something to balance the forces on the outside and the inside, right? And so if this mass here that you're putting on top is not going to change, then the force from the outside is going to be the same, right? Because as we said a couple of slides ago, the force from the outside is atmospheric pressure plus mg, right? And if this m is the same, then the force from the outside is the same. And so in this process, then then the pressure is going to be the same on the inside. But then how do we get it to expand in the first place? Of course, if you don't change this mass, then nothing's going to happen. So instead what we can do is add some heat. So if we add heat to the process, then the gas will expand. And by not changing this mass here, but adding some heat, we will induce this particular change. So it will expand, but it will expand at constant pressure. And so that's the first leg of this change. Now the second leg is when we're going to drop the pressure, but the volume's going to stay the same. Okay, so how do we firstly fix the volume? Well, what you can do is you can just fix the container size, right? So if we have this piston here, so we're starting at this configuration here, and maybe we attach some nails to the piston. Okay, then the volume will not change, right? That's constant volume. But we need the pressure to drop. How do we make the pressure drop? Well, we can cool down the system. That will drop the pressure. So put some ice cubes on the outside. Heat will leave the system, and then that will end up at a situation with a lower pressure, but then the volume is going to be fixed. So in terms of the work done, all the work done will be in this part of the process. So when this thing is expanding, this is when you're heating it up, it will actually, you've added heat to it, but it's also raised this object by some mass. So it's actually done some work. And that amount of work is, again, it's this integral of the P dV. In fact, in this case, because it's constant volume, the integral is simpler because it's constant pressure. Because it's constant pressure, all you have to do is just multiply the pressure by the change in volume. Yep. Okay, so now this time let's go a different route where we first drop the pressure and then increase the volume. So first leg is a constant volume process. So again, we do this trick where we pin the piston so that doesn't move anymore. But we need to drop the pressure, so we add some ice cubes. That will take heat out. It will reduce the pressure here. Then once we've got it to that point there, we need to increase the pressure. Here, what we need to do is actually adjust. We need to take the pins out because the volume is going to expand. And we need to adjust this mass here so that it's just the right mass, so that the volume is fixed. So we're going to kind of change this mass here so that it's got the right mass, so that it's the volume is the same. So that's why it's M prime here. And then we can increase the volume by adding some heat, and then it will expand. And in this leg, we don't change the mass on the top here by so that the pressure is constant. Pressure is always going to be balanced to be mg, m prime g, and atmospheric pressure. Okay. Okay, so that's kind of a little bit more of a idea of physically how you're doing this. So just to go through the remaining ones. So for the cycles, so I think I've more or less explained this already, but if you have a different path going forward or backwards, then in the forward leg it'll be a positive amount of work. So going from I to F is positive because, the integral will be positive. Going in the reverse direction from the final to initial, because you're integrating in the reverse direction, it will be negative. And if this is kind of like a different trajectory to the first one, then this negative value will be less than this one, and then so overall this will be a positive amount, and it's actually the area just between these two curves. So that's what happens in a cycle, and we'll come back to this cycle thing later, because an engine is really nothing but something where a gas goes in a cycle, and basically the purpose of an engine is that you are making the engine perform some work, right? So in an engine, basically the whole purpose is for the engine to provide some work to you, trying to get it to do something for you. And so in an engine, basically, you always have this kind of loop where the work will be, this is the amount of energy that you're sort of gaining by building the engine. Okay, well, I think maybe we'll just leave it there, and then we can do this as a revision next lecture. So, okay, so then, oh yeah, I've got a question.
Why do we adjust the mass in the previous slide? Yeah.
This stuff where adjusting the mass, yes, because here it was like I fixed the piston to be some volume, right? Now, if I just let go of the pins, now if I don't have the right mass, this thing will just sort of like either expand or contract to some different volume. And what I want to achieve here is at the end of here, I want to just go straight across here with the same constant pressure. So basically I need to adjust this mass so that it will be, at least at this initial point, the same height as where I left it. Yeah. Okay. Okay.